Hello and happy Valentine's Day. Since I'm not doing anything today for Valentine's Day, I decided to give a gift of Purdue love in the form of another Calc 3 video. So today we will be covering the Spring 2025 final exam. So this is pretty recent, so if you do well on this exam, you can expect to do decently well on the final relatively. Depends on how well you study. So let's get started with question 1. So question 1 asks us to find the tangent plane to the equation x minus 2 all squared plus 4y squared plus z squared equals to 5, and they want us to find this at the point 2, 1, 1. So let me help you visualize this, right? Imagine this is Slater Hill, it just snowed a lot. Imagine this is you right here. You have a very nice, very sled right there. And you want to place this very flat sled on the hill so that your feet touches the sled without slicing through the hill. So in order to do this, what you're going to want to do is take a little stick right here, pointing straight up, completely and perfectly perpendicular to the ground. And once you have that, you can lock your sled into perfect perpendicular place. So if you just listen to that and thought to yourself, what the heck is he talking about? Well, I'm talking about is the surface, and that stick is the normal vector. Whenever we're talking about surfaces, the normal vector right here, is always the gradient of the function they give us. So there's a few steps to doing question number 1. The first step is finding the gradient. The second step is finding the gradient at the point. I'll just call it P. And the third step is locking it into the plane equation, which I will just write out here. Plane equation. So now that we have all that set in, let's do that. So we have our equation right here. Let's just call this f equals to that. So in order to find the gradient, the gradient is simply just the vector of the partial derivatives of each component at their respective component. So let's evaluate each component. So f of x, when we're evaluating the partial derivative of f at x, you treat x as the variable and treat y and z as constants. So in this case, we just have to do a little bit of a chain rule. So for f, so bring the 2 down here, x minus 2, and evaluate what's inside, which would just be 1. And then for y is a constant, it becomes 0, and z is also a constant, it also becomes 0. So let's moving on to the partial derivative of f at y. In this case, y is the constant, so all we have to do in this case is evaluate what's right here, which would be 8y. And our last component, f of z, the partial derivative of f at z, in this case, z is our variable, so we evaluate z squared, which simply just gets us to z. Okay, so now we can build our gradient vector, which will be 2x minus 2, 8y, 2z. Let me fix that up. Okay, so moving on to step 2. Step 2 is evaluating at the specific point, which is just the gradient of f at point they gave us, 2, 1, 1. In this case, we just plug in our numbers. So if we plug in a 2 for x, we just get 2 minus 2. Plugging in a 1 for y, we just get 8 times 1, which is just 8. And plugging a 1 for z, you just get 2. So our gradient vector at the point they gave us will simply just be 0, 8, 2. Fantastic. And then the final step to getting this is to write it in the plane equation. So I'll write the plane equation up here in a different, actually I'll write it in black anyways. The plane equation, no, I'll write it in green, is ax minus x naught plus b y minus y naught plus c z, if I can spell, minus z naught, all equals to 0. And this a, b, and c is simply just the components of your normal vector. So that's the plane equation right there. Let's plug it in. So we know that in this case, since it's the components of the normal vector, and the normal vector is just your gradient at the point, you can plug that in. So a would be 0, which already takes out all the other parts of the a component of this equation, but we can put it in anyways. It would be x minus the point at 2, and then b would be 8 times y minus 1, because these are the points, plus 2, and that would be z minus 1, all equal out to 0. Okay, so when we distribute this, you get 8y minus 8 plus 2z minus 2 equal to 0. We combine like terms, you get 8y plus 2z is minus 10 is equal to 0. So all I can do is at this point is just move it over. You get 8y plus 2z is equal to positive 10. And then for this answer specifically, they want us to simplify the answer. In this case, I'll just divide everything by 2, which will get me 4y plus z is equal to 5. And if you look over at our answer choices, 4y plus z equals 5 is our answer choice F. So that is question 1. Okay, moving on to question number 2. So question number 2 gives us this rectangle, and it asks, let C be the counterclockwise boundary of the rectangle formed by the line segments from point 11 to point 41, 2.43, 2.13 back to 0.11. And they give us this nice little figure right here. Very nice of them. They want us to compute the line integral of the circulation, the flux of vector f times dr, where vector f is the components xy, x squared. Okay, so how I want you to imagine this is that let's say it's you again, you're walking along this boundary through a very windy field, right? The integral of this boundary adds up how much the wind pushes you along the path, which would be your circulation. So there's a hard way to do this and an easy way. The hard way is to calculate that circulation along all 4 sides and then add them up. But the easy way is to use a little formula that we like to call Green's theorem. Cheeky, huh? Okay, I think I spelled that wrong. Okay, so instead of walking along the edge, what we're gonna do is look at the curl inside the shape, and if we add up all the microscopic like curls, swirlings inside the rectangle, it equals to that total push. And guess what an integral does? An integral adds up every single possible little swirl. So I'm going to give you the formula for Green's theorem, which looks kind of weird at first, but it's the integral of p dx plus q dy equal to the double integral of the partial derivative of dq dx minus dp dy. And this is dA. So That's a strange looking formula when you first look at it, but there's a few pretty simple steps to doing this that I'll write out here. The first thing to do is to identify P and Q. The second step is to check the curl, and the third step is to solve the double integral. So let's get on to step 1. In this case, if we look at our equation here, our vector right here, our vector, P is going to be this xy, and Q is going to be x squared. So let's write that out. P is xy, Q is x squared. And the second step is to find the curl. So the curl of, let's say, curl f, as they would call it in the textbook, is the partial derivative of q with respect to x minus the partial derivative of p with respect to y. So if we take q right here and take the partial derivative with respect to x, you simply just get 2x. And if you take p and take the partial derivative with respect to y, you just get left with x, because x is the variable, y is the constant. You subtract these two, and you simply get just x. So what do we do when we set up the double integral? Well, just imagine it like this, right? You have the double integral, and it's the double integral of the curl of f dA. In this case, dA is simply just dx dy, or dy dx, depending on what you want to do. In this case, I will choose to stick with dx dy because that's what I did when I first solved the problem, but feel free to change up the order of integration if you find it more easy. So let's take a look at our order points right here, right? So if we go from the point x leftmost to the point x rightmost, it is 1 to 4. So we know that our first bound is from 1 to 4. And if we look at the y, it goes from 1 to 3, or right here, 1 to 3. So we know that our outermost bounds go from 1 to 3. You place the curl back in, which is just x, and we're going to integrate this dx dy. Sounds good? Okay, so let's integrate. So the first integration will be to just integrate x with respect to x, which just gets you x squared divided by 2. And we're evaluating that from the point 1 to 4 to 1. 4 to 1. So you plug in 4 squared minus 2 minus 1 squared over 2. Okay, so you have 4 squared over 2 minus 1 squared over 2, which will just get you 16 over 2 minus 1/2. That will just get you 15 over 2. Okay, so now, if we move over here, we have to now do the y part, which is from 1 to 3. We're integrating 15 over 2 with respect to y, which simply gets us 15 over 2y from 1 to 3 to 1. We can just write this out as 15 over 2, 3 minus 1, which is just 15 over 2 times 2. So these 2's cancel out, and all you get left with is 15. So if we look at our answer choices, that would be answer choice F. And that is question 2. Okay, moving on to question number 3. This is a vector field question. It asks, this figure represents a vector field. Which one could it be? Now, the first step I would recommend, which I'm just going to paste in here, is to write out your vectors. So I'm going to give you some time to write that out while I yap about vectors. So imagine this is a vector, right? all the components of a vector is that it tells you how much it goes in the x direction and how far up it goes in the y direction, up or down. So for this one, I'd say if this is vector v, the components of vector v would be positive x, positive y. Now, if you were to flip it any other way, this x and y would just tell you how far up or down it's going and how far left and right it's going. And you'll learn more about it in linear algebra, but we're on Calc 3, so I don't have to worry about that right now. Let me just place this up here. Okay, so we have all these vectors right here, and they correspond to these points, the vector f of x, y. So I bet I can get this done with one single point. So we're just going to look at our axes here, right? If you're going to do a vector field question, you should always look towards the axes first, because one of the points will be 0, because either x will be 0 here or y will be 0 here. So let's look at, let's say this point right here. This point, this vector, is at the point, is at the point, let's say 0, comma, positive 2. And the actual vector at this point is a negative x and a 0, y. Because as you can see, it goes in the negative direction for x, but it doesn't go up or down in the y direction for the y component. So when we plug in these points for all these answer choices, the correct one should match up. So let's look at answer choice A. Answer choice A says f of xy is equal to the component negative x, negative y. So in this case, when we plug in at this point, it will be f of 0, 2, and they say that at 0, 2, the vector should be negative x, negative y. Well, that can't be the case because our vector is a negative x and a 0, y, and if we plug in, I'll just write it out here. If we plug in, saw my pointer, f of 0, 2, you get the vector 0, negative 2. Simply doesn't make any sense. So it cannot be answer choice A. Answer choice B follows that same sort of rhythm, in which in this case they say that it should still just be 0, negative 2. So it can't be B either, and C follows the same sort of logic. It should also just be, but in this case it would be 0, 2, which still doesn't make any sense because we have a negative x component and a 0, y component. D, E, and F is where it gets a little bit more interesting, right? Because in this case, now we swapped the x component for the y component and the y component for the x component. This doesn't mean that they actually swapped. It just means that whatever you have in the y now represents the x, and whatever you have in the x now represents the y. Okay, so let's look at answer choice D. So for answer choice D, it says that at the point 0, 2, the vector field should be y, x. So let's look at that, right? So at 0, 2, but this time y is in the x part, so you get 2 in the x component and 0. Now this is so close to being correct. Unfortunately, as you can see, it's a negative x component, which means that D is incorrect, because as soon as they invalidate one vector field, it's not the same vector field. Now let's look at E. E has the components negative y, negative x. So let's look at that, right? We have at point 0, 2, the y would be negative, so we get negative 2, and the 0 is negative, but it's just a 0. If you look at that, that is correct. But we still have to look at answer choice F. So answer choice F has the vector field the vector y negative x. So at point 0, 2, this would be the point 2 negative x, which would simply just be 0. Oh, well, that can't be right either, because as I said again, this is a negative x component, which means that F is also not correct. So although we haven't checked every single point, all the other answers are incorrect. So in this case, we can only assume that the correct answer choice is E, which it is. So that is the vector field question number 3. All right, moving on to question number 4. So I look at question number 4, my first reaction is, what the heck is that vector? It says, let vector f equal to the inverse tangent of x over y, natural log of z minus 1, and y squared. It wants us to compute the gradient dotted with the gradient crossed with with the f component at the point 0, 1, 2. Now you might look at this question and you think to yourself, what the heck is going on? But allow me to remind you of a few properties, correct? When you have the gradient crossed with f, we call that the curl. When you have the gradient dotted with f, we call that the divergence. I'll just write it as div. This is a trick question designed to reward you if you understand your divergence curl properties. So imagine, if you would, this graph right here. The divergence of the graph is how much a fluid rotates. But the curl of a graph is how much a fluid rotates. Now that's a very bad drawing, but stay with me here. The divergence of a graph reviews how much a fluid compresses or expands. Now, if you just think about it, a purely rotating field cannot expand or compress. In this case, this is where mathematicians call upon this property right here, in which the divergence of a curl is always equal to 0. So, if you're actually doing this question and perhaps you didn't know all that about the concept of a curl, I would just recommend looking at this problem, realize how messy the curl of just the inverse tangent of x minus y would be, and then recall this identity right here. I'll write it out in the actual format. Is always equal to 0. So in this case, the answer would be answer choice B. And I hope if you ever come across a question like this, you realize and remember these properties, because this, if you compute all of it out, it would become 0, but you probably would have just taken 20 minutes for one question. So that's question number 4. All right, moving on to question number 5. Question number 5 asks us the velocity of a moving object for when t is greater than or equal to 0 is r prime of t equals to 60, 96 minus 32t. So they want us to find r of 1 if the initial position is r of 0 equals to 0, 3. So let's write out what we know. They know that when r is equal to 0, it's the component 0, 3, and they want us to know what is r when t is equal to 1. So if you look at this right here, r prime of t is our velocity. That's our velocity right there. Velocity is the rate of change of position. In other words, velocity is simply just the derivative of position, in this case, which is r of t. So when you have velocity, the derivative, how do you get back to position? You do the opposite. You simply integrate velocity. So we're going to integrate r of t with respect to t. Now there's one other thing you should understand, which is that because this is what we call an indefinite integral, whenever we get whatever the answer choice is, we always have to add on a c, because there's going to be an accumulated change that we don't account for with the integration, so we add on a constant c to make sure we account for that. So let me work you through this, okay? So if we take the integral of r of t with respect to dt, that is essentially the same as taking the integral of all the components with respect to t, just like this. Oh, where'd my minus sign go? So let's do that. That means r of t is equal to the integral of 60 with respect to t, which simply gets us 60t. Remember to add that c. I'll label this c1. And this will be comma 96, which just becomes 96t, minus, this will become 32t. So t squared divided by 2, which gets you 16t squared. Remember to add that c. Okay, so now we have our base formula for the position vector. Let me take this right here and put it over here. But now we still have these constants, and we have to find out what the constants are. But luckily, they gave us these points, so we can actually plug in a 0 for t and equal both of these components to their respective components, 0 and 3. So when we plug in r of 0, we're assuming that t is now 0, so 60 becomes 0 plus c1, but that is equal to 0. So now we know that c1 is equal to 0. On the flip side, when t is now equal to 0, you get 0 minus 16 times 0 is 0 plus c2, which is equal to 3. So now we know that c2 is equal to 3. So when we rewrite our position vector, it's simply 60t comma 96t minus 16t squared plus 3. Incredible. So now we move on to our final step, which is plugging in r of 1. So when we plug in r of 1, you simply get 60. Now if you look at our answer choices already, that takes out A and that takes out C. Well, we gotta do the rest. You get 60, and then everything just times 1, so 96 minus 16 plus 3. 96 minus 16 plus 3 is simply just 83. So r at 1 is simply just the vector 60, 83, which aligns with our answer choice F. And that, ladies and gentlemen, is question number 5. Okay, moving on to question 6. So, question 6 is Question 6 is a tough problem. I'll be very upfront with that. It is a hard problem, but luckily, they give us the hint to use Stokes' theorem, which is good. So question 6 says, let S, the surface, be part of the hemisphere. Z is equal to 4 minus x squared minus y squared, that is inside of the cylinder, x squared plus y squared equals 1. So if the vector f is equal to yz, negative xz, yx, compute this flux integral, where the normal vector to the surface S is oriented upwards. And they want us to use Stokes' theorem. That's a whole lot of words, but I'm going to try to simplify this as much down as I can. So the first thing is we're going to look at this right here. Z is equal to the square root of 4 minus x squared minus y squared. Now, the first thing we're going to want to do is find out what z is. And we actually have it already right here. There's an x squared minus y squared right here. We know that x squared plus y squared is equal to 1. So if we just do 4 minus, put this parentheses here, x squared plus y squared, all square root, then we say that z is equal to the square root of 4 minus 1, which is the square root of 3. So now we know what z is. The second step is to parameterize the curve. So we know that since it's a circle, x is going to be cosine t, y is sine t, and we just found out that z is the square root of 3. And it's a circle, cylinder, they're not cutting off any part of the circle, so we know that this is going to be from 0 to 2 pi. Okay, so we'll call this step 1, call this step 2. Step 3 is finding dr. Okay, so in order to find dr is our velocity vector. And luckily enough, for velocity vector, we just put this in. So we know that r of t is equal to the components cosine t, sine t, and square root of 3. So in this case, the velocity vector is just the derivative of the position vector, which means that r prime of t is just the derivative of all the components, which is just negative sine of t, cosine t, and square root of 3 is a constant, so it becomes 0. Okay, so that was step 3. Told you it's a long problem. Step 4 is to evaluate f on the curve. So in order to do this, we have f is equal to yz, negative xz, and xy. So what we're going to want to do is to evaluate the vector f on the curve, you plug in r of t, which basically gets us y times z will be is that x times z or y times z? Yeah, that's y times z. Is going to be sine of t times square root of 3. Negative x times z is equal to negative cosine t times square root of 3. And xy is going to be equal to cosine t times sine of t. Okay, so due to this, we know that our vector f is going to be square root of 3 sine t, negative square root of 3 cosine t, and cosine t sine t. Incredible. So that was let's say that's step 4. Let me actually just highlight these for you. Step 4. That was step 1. This is step 2, step 3, step 4. And step 5 is to calculate the dot product of vector f times dr. Okay, So we're going to be multiplying vector f times dr. So let me just yank this real quick. This will be this vector. I'm sorry, I'm going to have to make this a bit smaller now. This vector times this vector. So I'm just gonna go here real quick. If we do the dot product of vector f times dr, you get negative square root of 3 sine squared t. Whoa, this should not have the vector sign. Plus, oh, that should be a minus actually. Minus square root of 3 cosine squared of t plus 0. Now, we can use a common trig property to integrate this. Sorry, not integrate this, because we know that sine squared of anything plus cosine squared anything is always equal to 1. So we can pull out the negative root 3 to get sine squared t plus cosine squared t. So in the end, we just get negative square root of 3. Let me move this down. Okay, last step, step 6. Step 6 is just a single integration. We're going to integrate across the circle from 0 to 2 pi of negative square root of 3 dt. Once we do that, you get negative square root of 3t times 2 pi minus 0, which simply gets you negative 2 pi square root of 3, which in this case, if we look at our answer choices, that is simply just answer choice B. So this is a very long problem. It's a very, I'd say even it's a pretty tough problem. It's a very challenging one. But if you can break it down into these little parts and then put it all together, you will do great. So that was question number 6. Okay, moving on to question number 7. Question number 7 says, the graph below shows a curve on a circular cylinder. Which of the following vector-valued functions could describe this curve? Okay, so I want you to just look at this curve real quick and notice that the x and the y and the z, usually when you see one of these, you might think, oh, the x is the cosine, the y is the sine, and the z is the constant, so it makes this cute little cylinder. But in this case, they flipped it on its head. So now, if we were to draw this out like this, this is the cylinder we're working with now. So instead of y being the sine, they're most likely going to make z the sine and y the constant because it's moving up in the y-axis. So just knowing this, we can actually check off a few answers. So for some of these, you might just want to be able to know. I think this question relies very well on just knowing that the shape should be a cosine t, t sine of t variation. So if we look at A, it can't be A, because if it was A includes a sine 2t. Oh, and this also goes for F. It can't be F. It can't be A or F. It includes a sine 2t. A sine of 2t often creates a figure, I can't draw, often produces a figure 8, like an infinity symbol, whenever graphed. So we already know it can't be this, can't be A, can't be A or F. And if we look at C, C is cosine t, sine t, t. Now, this is our usual circle, but for C, it's wrong because it's assuming that in this case, the circle is moving up in the Z direction, so it can't be C. For D, D is so very close. Unfortunately, they include these T's, not that one, these T's in front of the cosine and the T, which means that it wouldn't actually be a cylinder. Instead, because there's the T there, the T changes the amplitude, which is just like the amount, and instead of being a cylinder, it becomes a tornado shape, right? Oh my lord. So it can't be D. And then between E and F, my bad. Between B and E, we just look at B and E. B matches what we have. E has a T in the X direction, which means that what E is supposing is that it's now a cylinder in the X direction. I'm so sorry, I'm very bad at drawing. But in this case, we know that it can't be E, and thus it has to be B. So that is question number 7. All right, moving on to question number 8. Question number 8 asks us to compute the net outward flux of the vector F across the sides of this box, where X is from 0 to 1, Y is from 0 to 2, and Z is from 0 to 3. And there's a hint. It says there's a better way to do this problem than computing 6 flux surface integrals. And whoever wrote this was very correct in saying this because I almost would have done that. That's just a joke. Okay. So, in this case, we use the divergence theorem. For the divergence theorem, I'm on my highlighter. It uses this formula for flux, which is the triple integral of the divergence dv. So, how do we do this? Well, with all good things in Calc 3, the first thing we gotta do is calculate the divergence of f. So, what is the divergence of f? Well, it is simply the partial derivative of p with respect to x plus the partial derivative of q with respect to y plus the partial derivative of r with respect to z. Now, you might be asking, what is p? What is q? What is r? Well, these are simply just the letter variable names that we assign to each component. So it just goes in order. That's p, that's q, that is r. So now we have to simply find the partial derivatives of each of these with their respective variable. So let's do the partial derivative of p with respect to x. In this case, this means that we're taking x as the variable and y and z as the constants. So in this case, if we look at this, they want us to follow the product rule, but since y is a constant, there's not really too much product rule to do. So all we're going to do is actually, I can write this better. I'll write this as just like this, d over dx of 2y cubed x squared plus z squared. We imagine this as y just being a constant. So in this case, since z is just a constant, it becomes 0, and we actually just get left with 2y cubed times 2x. Now if we do the same thing with q, get x e plus z minus xy to the 4th. That e to the power of x plus z just becomes 0 because those are both constants, which means we just get negative 4x times y cubed. And the final one is d of dz of 2z minus the square root of x squared plus y squared. In this case, x squared plus y squared are both just constants, so they become 0. And then the z, we just take the derivative, the derivative of 2z just gets us 2. So now in order to find the divergence at f, man, I can't talk today. We just sum all these together. So sum up 2y cubed times 2x plus, we can actually break this down into 4xy cubed. And that will be minus 4xy cubed plus 2. Which means that through all that math, the divergence of f, this huge vector, is just 2. Incredible. So in order to now find the divergence, you compute this triple integral. If we look at it, they actually already gave us the triple integral right here. So what we're going to do is let's just do it in the order they gave us. X, and then y, and then z. So x goes from 0 to 1, y goes from 0 to 2, z goes from 0 to 3. So if we do this, dx, dy, dz, you simply just get 2x from 0 to 1, gets you 2. And then if you take the integral with respect to y, to dy, you get 2y from 0 to 2, which simply gets you 2 times 2, which is just 4. And now you take the integral with respect to z, so 4 dz, which gets you 4z computed from 3 to 0, which is just 4 times 3, which gets you the answer choice 12. So if you look at our answer choices, answer choice C is equal to 12. Now, there is one other way you could do this a little bit quicker, but it's only really if you know how to do it like on the spot. You know that your box dimensions, if I draw this out right here, it's 1, goes from 1 to 2, z to 3. So it's this box right here. And the box dimensions are simply just 2, 3, 1. So if we take the volume of that, it's just 3 times 1 times 2, which is 6. And if you really knew how to do it in the moment, another way to do this is to just take the divergence times the volume, which in this case is just 2 times 6, which gets you 12. But only really do this with these simple shapes. If you get something like, I can't even name anything because I was bad at geometry, but with these simple boxes and like circles, yeah, go for it. But that was question number 8. Okay, moving on to question number 9. Question 9 asks us, D is the ball of radius 1 centered at the origin. Compute the outward flux vector F is equal to x times y squared I plus yz squared j plus zx squared k across the boundary of D. So this is a classic divergence theorem question. We have to compute the triple integral of the divergence of f dv. Okay, so this is actually the same kind of question as question 8. They just made it a bit longer and they're using spherical coordinates now, which we'll get to. So the first step, as always, with all good things, is to calculate the divergence. So we know that vector f has the components x, y squared, y, z squared, and zx squared. So in this case, if we take the divergence of vector f, you simply take the partial derivative of each component with respect to x, y, z, depending on which component it is. So for the first component, it's with respect to x, you get left with y squared. Sorry, should have no vector right there. plus the partial derivative of f with respect to y, in this case, which is just z squared. And then the last one is the partial derivative of f with respect to z, which is just x squared. Now, I can rearrange this into x plus y squared plus z squared. And you might look at this and say, wow, that is actually the exact same formula for rho squared. Now, you might be wondering, what does this have to do with anything? Well, you're actually so close to already being there. All we have to do is set up the integral now. dv with any spherical coordinates will always be this. It will always be rho squared times sine of phi d rho d phi d theta. I would like to emphasize how much you should know this. This is a very important dv to know, but our integrand is rho squared. So we put this in rho squared times rho squared sine phi d rho d phi d theta. And for our actual integration bounds, this is a ball of radius 1, which means that if we had this, for example, had this right here, that's the rho, and the radius is equal to 1, which means that rho is just equal to 1 in this case. So it goes from 0 to 1. And there are no other specifications given to us. So in this case, the integration bounds for phi would just be from 0 to pi, as we know, and from 0 to 2 pi for the circular part. Okay, so now we have this very long triple integral, but we can do it. So let's integrate with respect to rho first. So we get rho to the 4th from 0 to 1. I'm going to take sine phi out first because it doesn't really have any part in this. And we're going to integrate with respect to rho. So if we were to integrate with respect to rho, you get rho to the 5th over 5 from 0 to 1. It's 1, 0. Just get to 1/5. Okay, now comes phi. So sine of phi integrated from 0 to pi d phi. I'm going to leave the 1/5 out here. Oh, my bad. The integration of sine is negative cosine. So in this case, we integrate, we get negative cosine of phi, 0 pi, which gets you negative cosine of, whoopsie daisy, of pi minus negative cosine of 0. Negative cosine of pi, cosine of pi is already just negative 1. So we just get left with 1 minus negative 0. I cannot speak today. Cosine of 0 is 1, so that would just be negative 1. So you just get 1 plus 1, which is 2. Okay, so now we have 2/5. Whew, man, that's a lot. But one final integration. We got to integrate d theta. And theta goes from 0 to 2 pi. There's no theta to worry about, so you just get 2 over 5 theta integrated 0 to pi, which simply gets you 2/5 2 pi minus 0, which is just 4 pi over 5. 4 pi over 5, which is our answer choice B. So that was question number 9 using the divergence theorem and spherical coordinates. All right, moving on to question number 10. Question number 10 asks us to compute the line integral of the integration of the surface C, line segment C, of negative y dx plus x dy plus z dz, where C is the line segment from the point 212 to the point 844. So there's a couple steps to doing this question, but the first step that you should always think about is to parameterize. So we need to parameterize. In this case, they already gave us 2 points. So how we're going to parameterize, we're going to call this P naught, call this P1. So how do you parameterize? Well, in this case, our R of T is going to be equal to P naught plus, sorry, that looks too much like an actual T, plus T of the vector V1 minus P naught. And for all line integrals where we parameterize a line, the bounds will always be from 0 to 1. Okay, so let's parameterize. P1 minus P naught. So in this case, you get 8 minus 2, 4 minus 1, and then 4 minus 2, which gets you 6, 3, 2. So P naught is 2, 1, 2, plus the vector T times 6, 3, 2. Incredible. So how am I going to pull this out? Well, I'm just going to say in this case, x of t is equal to 2 plus 6t. Y of t is equal to 1 plus 3t. And z of t is equal to 2 plus 2t. Then the next step for plugging this in is we need to find the differentials, which sounds weird, but it's actually just taking the derivative of each of these components with respect to t. So for example, for this one, you'll just get 6. For this one is 3. This one would just be 2. Okay, so for our big step, it's substituting everything back into the integral. So when we do that, we have our integral right here. It's negative y dx, so y is 1 plus 3. So you get negative, whoops, I should probably write it out here, negative 1 plus 3t times dx, which is 6, plus x, which is 2 plus 6t times dy, which is 3. And that's plus z dz, which in this case is just 2 plus 2t times 2. Okay, now we gotta simplify the integrand, as they like to call it back in the day. The integrand, which just becomes negative 6 minus 18t plus 6 plus 18t plus 4 plus 4t. So as you can see, these two cancel out, and we simply get left with 4 plus 4t. And now we just have to compute the integral with the bounds we already know, 0 to 1 of 4 plus 4t dt. I'm actually going to move this over here. But when we evaluate this with respect to t, you get 4t plus 2t squared, 0 to 1, which simply just becomes 4 times 1 plus 2 times 1 squared, which is simply just 6. So in this case, our answer is answer choice F. And that is question number 10. All right, done with the halfway point. Moving on to question number 11. Question number 11 asks us to consider the limit as x and y approaches 0 to 0 of x times y over x squared plus y squared. And it asks us which of the following statements is true? So with this kind of question, you want to consider the paths. Sorry, my writing's a bit slow. You want to consider the paths. So what you should always know is that using the path method, you can approach from an infinite amount of direction. So with paths, you can always test for if the limit doesn't exist, but you can never test for if the limit exists. So in this case, this will be our strategy. Okay, so the first thing we want to just get out of the way is just use the points they already gave us. So in this case, if we use 0, 0, you just get 0 times 0 over 0 squared plus 0 squared, which just gets us 0 over 0. Okay, so now we're going to test the first path. Test path 1, which in this case will just be, let's just say y is equal to 0. So in this case, it'll be limit x and y as it approaches 0, x and 0 as it approaches x comma 0, which simply gets us x times 0 over x squared plus 0 squared, which just gets you 0 over x squared, which is just 0. Okay. What if we did x equals 0 in this case? So the limit as x and y approaches 0, y, you just get 0 times y over 0 squared plus y squared, which just gets you 0 over y squared, which is also 0. Okay, so far so good. Both axes say the answer is 0. Now let's test this, y equal to x. So in this case, the limit of x and y as it approaches x comma x, which gets us x times x over x squared plus x squared, which gets us x squared over 2x squared, which is in this case 1/2. So since 0 doesn't equal 1/2 in this case, we already have paths that have restricted limits. So let's already look at some answer choices that can't be correct. Well, it can't be B because it says the limit is 0. Can't be C because it also says the limit is 0. And it cannot be E because it also says the limit is 0. Okay, so now let's look at this. A, it says limit does not exist. Okay, that's correct because the path restricted limit approaching 0, 0 along the diagonal y equals x does not exist. Well, that's not true. We already found that approaching y equals x, it exists as 1/2, so it cannot be A. And then it says for the limit does not exist for D, because the path restricted limits approaching 0, 0 along the x-axis and y-axis are different. Well, that's not correct either because we found that both of them are 0, so it can't be D. And then for F, it says the limit does not exist even though the path restricted limits approaching 0, 0 along the x-axis and y-axis are both 0. And in this case, that is our correct answer, answer choice F. So that is question number 11. This is a limits question. Test your paths. Okay, moving on to question number 11. So question number 12. Question number 12 asks us to find the equation of a plane containing the points 1, 1, 1, 1, 2, 3, and 3, 1, 0. So I want you to imagine it like this, right? I'm going to draw this out for you guys. Imagine you have a plane like this. you have a plane like that, right? Imagine you have points just like this, and they're vectors, you know? They're vectors. In order to find and define this flat plane, you need a normal vector. So a normal vector is a vector that points directly perpendicular from the plane. If you have these 3 points as corners of the triangle, if you take 2 sides of this triangle, which are 2 vectors, and calculate their cross product, the result is a vector that will point perfectly away from the surface. So if we want to find this normal vector, all we have to do is find the cross product of these points. But currently, these are just points. So how do we create a vector? Well, I'll define this point set as P, this point as Q, and this point set as R. Now we can actually make vectors. So, going from P to Q, you get 1 minus 1, so this should be a vector notation, 2 minus 1, and 3 minus 1, so which gets you PQ is equal to, why did I write a 0 there? 0, 0, 1, 2. Now do the same thing with R, PR, which gets you 3 minus 1, 1 minus 1, and 0 minus 1, which gets you the vector 2, 0, negative 1. Now we can find our normal vector. Our normal vector is that cross product of P and Q. So if we set up our cross product right here, you get 0, 1, 2, and 2, 0, negative 1. So in this case, we'll compute our cross product. We'll cross, it'll be negative 1 minus 0, because 0 times 2 is 0, and that'll be for the I. Now remember, this is a negative, not a positive, sorry, a subtraction symbol, not a addition. I feel so stupid saying that. 0 times negative 1 is 0, 2 times 2 is 4, so it'll be negative 4. J plus now, 0 times 0 is 0, 2 times 1 is 2, so it'll be minus 2. This will be K. So our vector for this will be the vector negative 1, positive 4, because of that subtraction symbol, and negative 2. That is our normal vector. Okay, now that we have our normal vector, we can just write the equation of the plane. Remember, the equation of a plane is A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught, all equaling to 0. And remember, A, B, C is simply just the components of your normal vector. So we have to choose a point to use, so let's just go with the quick and easy point P. So let's set this up. That'll be negative 1 x minus 1 plus 4 y minus 1 minus 2 z minus 1. That all equals out to 0. Once you do all the math for this, you get negative x plus 1 plus 4y minus 4 minus 2z plus 2 is equal to 0. And then once you once you add like terms, you get negative x plus 4y minus 2z plus 1 is equal to 0. So if we transfer this over, you get negative x, sorry, should be a my plus. Wait, am I correct? I think I may have done my math wrong here. 1 minus 4, negative 3 plus 2, negative 1. Yeah, I was wrong. And then in this case, you just get negative x plus 4y minus 2z is equal to positive 1. But if we look at our answer choices here, the one that fits clearly wants x to be positive, so we just multiply everything by a negative 1, which gets us x minus 4y plus 2z equals to negative 1, which in this case is answer choice B. This is one of those cases where you get the final answer and you just have to look around for which one matches, and then if it's the same answer choice but with just all the signs flipped, then you know that's just the correct one. So this is answer choice. Sorry, this is problem number 12. All right, moving on to question 13. Question 13 is a directional derivatives problem. Directional derivative. So it asks us, how did I spell that wrong? It asks us to find the derivative of the function f of x, y, z equals to x times y times z in the direction I minus 2k at the point 1, 2, 3. Okay, so what you're going to want to do for this problem, for a directional derivative, you need two things. You need a gradient, in this case, gradient f. And for the directional derivative, you need a unit vector. So in this case, they gave you that direction for the unit vector, and they gave you this function for your gradient. So you have it all figured out. So remember, for the gradient, what you're going to want to do is take the partial derivative of each component with respect to x, with respect to y, with respect to z. So in this case, x times y times z with respect to x is simply just yz. X times y times z with respect to y is just xz, and with respect to z, it's just xy. Now, we're going to want to compute the gradient at point 1, 2, 3. Once we do that, you get 2 times 3, 1 times 3, and 1 times 2, which gets you the gradient 6, 3, 2. Okay, so now you have your gradient. Moving on to the next thing, which is to normalize your direction vector and find its unit vector. So we already know that our direction vector, I'll just call it v, has an I, so it has a 1 for I, no j, which means it's 0, and k, it has a negative 2 coefficient, so I'll just put a negative 2. In order to find the unit vector for this, remember, a unit vector is the vector divided by the magnitude of that vector. So we gotta find the magnitude first. So the magnitude is the square root of all components of the vector squared and added together. So this will be 1 squared plus 0 squared plus negative 2 squared, which turns out to be square root of 5. So for our unit vector, that would simply just be 1, 0, negative 2, all over square root of 5. Okay, now the final part of finding the directional derivative is actually this. The formula for the directional derivative, which I now realize I probably should have given you, which is a big oversight on my part, I'm so sorry, is duf, that's the directional derivative symbol, which is the gradient of f times its unit vector. So guess what we have? We have our gradient of f, and we have our unit vector. Let's go to town. This is a simple dot product. It'll be 6, 3, 2 times 1 over square root of 5, 0, and negative 2 over square root of 5. So when we dot these, you get 6 over square root of 5 plus 3 times 0 is just 0. So you get 0 minus 4 over square root of 5. So in this case, you just get 2 over square root of 5. In that case, 2 over square root of 5 is our answer choice A. And that was question number 13. Okay, moving on to question 14. Question 14 asks us to find the area of the surface z equals x squared plus y squared when x squared plus y squared is less than or equal to 1. So just right off the bat, you just look at that and you just know that is a circle right there. That is a circle. But they want us to find the surface area. Now, in order to find the surface area, there's 2 to 3 main methods. But there's one method, which is when they explicitly give you x and y, in which you can use the formula, the square root of the partial derivative of x squared plus the partial derivative of y squared. This is what we call a stretching factor, but that's not entirely important. In order to find this factor, let's first find the partial derivative of f at x. Or you can also just call it the partial derivative of x at z. Z with respect to x. But I'll call it f in this case. In this case, that'll just be 2x. And for y, same deal. 2y. Okay, so let's put this in. In this case, when we substitute all these values in, you get 1 plus 2x squared plus 2y squared. Well, what does this get us? This gets us 1 plus 4x squared plus 4y squared. Now, I'm sensing something that I can factor out. Aha! You can factor out this x and this y, which gets you 1 plus 4x squared plus y squared. Ho, 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 ho. I don't know why I made that sound. Okay, anyways, we're going to keep this here for now. We're going to move on to setting up our integral, right? So, we know from polar coordinates that x squared plus y squared is equal to r squared. And we know that for polar coordinates, our dA is r dr d theta. So, in this case, this x squared plus y squared just becomes an r squared. So when we do this, they are actually already told us, let's compute our bounds. So we know that x squared plus y squared is less than or equal to 1. X squared plus y squared is the same as r squared less than or equal to 1. So now we know that our radius is 1. So our radial bounds go from 0 to 1. And this is just a regular circle. So our theta bounds are from 0 to 2 pi. Now we already have our integrand right here. So let's just plug it in. That'll be 1 plus 4r squared. Don't forget that r dr d theta. Okay, so now we can solve this. Our first step to solving this is a classic case of a u substitution, which in this case, we'll take our u as 1 plus 4r squared. In that case, our du will be equal to 8r dr. So that basically means that when, du is r dr is equal to 1/8 du. So now we have to change our limits. We're going to plug this in. So when r is equal to 0, u is equal to 1, oh my lord, 1 plus 4 times 0 squared, which is just 1. And then when r is equal to 1, whoa, what's going on with my handwriting? When r is equal to 1, u is equal to 1 plus 4 times 1 squared, which is just 5. So now we can reset up our equation. So now the bounds are from 1 to 5, square root of u du. Oh, and don't forget the 1/8 out there. So using this, that u becomes 2 over 3, u 3 over 2 from 1 to 5, which simply just becomes 2 over 3, and then 5, 3 over 2 minus 1. 1 to the power of anything is just 1, so we just get 1. Don't forget that 1/8. So you just get 2 over 24 times 5 to the power of 3/2 minus 1. So that is our first integration, but our second integration, we still need to integrate from 0 to 2 pi 1. I'm just going to call this 1/12. I'm going to simplify it down. 5 to the power of 3/2 minus 1 d theta. Since there's no theta whatsoever, we just multiply it by our bounds. In this case, that's just 2 pi, and the 0 just turns everything to 0, so it's just 2 pi. So I'll put 2 pi here times 12 times 5 to the power of 3/2 minus 1. And if we simplify it down, you get pi over 6 times 5 to the power of 3 minus 1 minus 1, which in this case gets us the answer. If I'm kind of running out of space here, but gets us the answer 5 to the power of 3 over 2 minus 1 times pi all over 6, which is our answer choice F. Terribly sorry, my work got a little bit messy there at the end, but that's question number 14. Okay, we're going to be moving on to question 15. Question 15 asks us, let C be the boundary of the triangle formed by the portion of the plane t equals 6 minus 3x minus y in the first octant, oriented as shown in the figure below. Compute this integral for the vector field f is equal to the components y plus 2x, negative x, and negative 2x. And it says to use Stokes' theorem. Okay, this is a very big problem, but it's very doable, which is why I'm going to show you the certain things you're going to want to figure out when you're doing this problem. A few things you're going to need to do. Find the curl, find the normal vector of the surface, integrate over the shadow of triangle, and find your answer using that. So first thing we gotta do is find the curl of f. Curl, which in this case is just f, the gradient cross of f. We have our f right here, so let's get to work. So in this case, the curl, if we set it up, I, j, k, d over dx, d over dy, d over dz. This indicates that we're going to be taking the partial derivatives, so y plus 2z, negative x, and negative 2x. So when we calculate this out, we get, so the partial derivative of y with 2x is just 0, same with 0, so our I has nothing. So the partial derivative of negative 2x with respect to x is just negative 2, and with z, it's also just positive 2, so you get negative 2 minus 2, so that's our j, and this would be plus d over dx, the derivative with respect to x is just negative 1, and for y it'll just be positive 1, so you just get negative 1 minus 1, that's our k, so we know our curl in this case is 0, 4, because that's negative 4 times the negative plus negative 2. That was already a lot of work, but there's more. Bah! Okay, so the second part is to find the surface normal vector, which in this case is our ds. In order to do that, we have this plane right here. Z is equal to 6 minus 3x minus y. And the little trick that my lecturer taught me last semester is that if you have this z, and in this case, the normal vector is always going to be the vector of negative partial derivative of z at x, negative partial derivative of z at y, and then a 1. So let's do that. The partial derivative of z at x is negative 3. But because it's negative, we just get 3. The partial derivative of z at y is negative 1. But since it's negative, we just get a 1. And then we add in the 1 right there. So we already know our normal vector. Okay, now we're going to have to do the dot product between our curl and our normal vector. So that's going to be our curl dotted with our normal vector, which is 0, 4, negative 2, dotted with 3, 1, 1, which gets us 0 times 3. I don't know why I keep putting those vector symbols. Plus 4 times 1 plus negative 2 times 1, which simply gets us 2. Okay, now this is the last super big chunk of this, which is the integrate over the triangle using the area of the shadow of the triangle. So how do we do this? It's sort of weird to wrap your head around it, but I'll try my best to explain. In this case, you're imagining that you're integrating over this triangle right here, and then you move up as you go through it. So because we're integrating over this shadow right here, you set z equal to 0 because z is equal to 0 in that triangle. So in this case, what you get is when z is equal to 0, you get 0 is equal to 6 minus 3x minus y. So you just get y is equal to 6 minus 3x. Okay, so now that you have y is equal to 6 minus 3x, the next thing you should do is identify that in order to solve this problem, an actual integration, a triple integration using dx, dz, dy, dx is simply not time effective, and this is one of those questions where you should call upon the formula of multiplying the integrand by the area. In this case, that area is just this triangle. So how do we do that? Well, the area of a triangle is just base times height over 2. How do we find that? Well, let's find the intercepts first. So to find the first x-intercept, you said y equal to 0. So you get 6 minus 3x. Thus 3x is equal to 6. Thus, the first intercept is at 0, 2. So we know that this base length is 2. Now I have to find the height. That's when x is equal to 0. So now we know that y is just equal to 6 because x is 0. So now we know that the second intercept, I don't know why I wrote it like that, is at 0, 6. So we know that this height is 6. So in order to find the area of this triangle, you just do 2 times 6 over 2, which gets you 6. And then in order to finally finish out this question, you simply just do 2 times 6, which is the area, which gets you the answer choice 12. Now, that was answer choice E. Now, although this question is very long, it seems very tedious. In this case, I would heavily suggest reviewing over all the different ways they've taught you to figure out surface integrals, to figure out how to do triple integrals and when the steps to take. This is one of those simple little tricks that could save you so much time whenever you're taking a test, so rely on these sorts of tricks. In this context, this is question 15. All right, moving on to question 16. Question 16 asks us, find the volume enclosed by the surfaces t equal to x squared plus y squared and z is equal to 12 minus x squared minus y squared. So here's how I want you to imagine this, right? Think there's two bowls. Z equals x squared plus y squared is the first bowl. It's just sitting upright like this. And z equals 12 minus x squared minus y squared is the second bowl. And it's flipped upside down. So it doesn't necessarily have to look like that. But this is a representation of what these two could look like. So we're trying to find the amount of space that's trapped between them. And to find this, we subtract the bottom bowl from the top bowl and add those differences over the area where they overlap. So how do we do this? Well, the first step is to find the intersection. That is also equal to the rim. Call this the rim. In this case, we set z's equal to each other, which means we get x squared plus y squared is equal to 12 minus x squared plus y squared. If we move everything to one side, you get 2x squared plus 2y squared is equal to 12. Divide everything by 2, you get x squared plus y squared is equal to 6. So, since we know that x squared plus y squared is equal to r squared, we also now know that r is equal to the square root of 6. Okay, so how do we find the height difference? Well, now in order to find the height difference, we subtract the top. Remember, this is our top. We subtract top minus bottom. In this case, our top will be 12 minus r squared because it'll be, imagine this, 12 minus x squared plus y squared. So 12 minus r squared minus just r squared again, which just gets you, oopsie daisy. That'll be 12 minus r squared, which just gets you 12 minus 2r squared. Sorry, I had a brain fart right there. But now we just have to find the volume. So we already know our radius, and this is just a circle. So our bounds will be for the radius 0 to square root of 6, and for the theta 0 to pi. Let me move over here so we have a bit more space. But we already have our integrand right here. That'll be 12 minus 2r squared. So to make this clear, this step here was in order to find the radius. This step here was to find the integrand. So let's do this. That's 12 minus 2r squared. Remember, r dr d theta. Okay, so I'm now gonna show you guys a little tip that I haven't actually reviewed this entire session yet, which is that when you look at this and you see that you have a dr here, but there's not a single theta in sight, what you can actually do is just think of it like this. Now you just have from 0 to 2 pi of d theta times 0 of square root of 6, 12 minus 2r squared, r dr. And because that d theta is just the 2 pi, now all you have to think about is it's just 2 pi times the integral from 0 to square root of 6 of 12 minus 2r squared, r dr. So that's a little trick you can do at the very start just to make life a little bit easier and not have to look at all those integrand parts. So now let's integrate this. You get 12r minus 2r cubed from 0 to square root of 6 dr. Once we integrate that, you get 6r squared minus r to the 4th over 2, and we're evaluating that from 0 to square root of 6. So we plug in square root of 6, you just get 6 times square root of 6 squared minus square root of, square root of 6 to the 4th over 2, which simply gets you, sorry, my bad, I choked on something, simply gets you 36 minus 36 over 2, which is just 18. Now that you have 18, you simply bring the 2 pi back to get 2 pi times 18, which gets you the answer 36 pi, which in this case is our answer, choice D. So that is question 16. All right, moving on to question 17. We're in the home stretch now. Question 17 asks us to find the area of the region D is equal to r theta, where theta is between 0 and 2 pi, and radius is in between 0 to 3 plus sine of theta in polar coordinates. So what basically just happened is that they did half of the work for us, so we just need to set up the integral and do the work for it. That is incredible. So let's set up the integral. So we already know that r is from 0 to 3 plus sine of theta, and theta is from 0 to 2 pi. Okay, well, what about our dA? In this case, our dA is just r dr d theta. So let's just write that in. So let's solve for r first. When you integrate with respect to r of r, you just get r squared over 2, integrating from 0 to 3 plus sine of theta. Okay, this might be some lawn math, but I'm going to pull the 1/2 out. So I'm going to do this down here. I'm going to pull the 1/2 out, and this simply returns us, this will be 3 plus sine of theta squared over 2, which just gets us 9 plus 3 sine theta plus 3 sine theta plus sine squared theta, which simply gets us 1/2 times 9 plus 6 sine theta plus sine squared theta. It's very fun integral, but we got this. What I'm going to do now is I'm going to split up each piece respectively. So we're going to keep the 1/2 all the way out here, do an integral from 0 to 2 pi of 9 d theta plus the integral of 0 to 2 pi of 6 sine theta plus d theta plus the integral from 0 to 2 pi of sine squared theta d theta, and that will get us our final answer. So when you take the integral of 9 d theta, you just get 9 2 pi minus 0. This gets you 18 pi. For 6 sine of theta, you get negative 6 cosine of theta. Cosine of theta, and that'll be negative 6 cosine of theta between 2 pi and cosine of 0. So cosine of 2 pi is just 1, cosine of 0 is just 1, so it's just 0, so you just get 0. And then here's the big one. If we use our hint right here, the hint that they so graciously gave us, which is that sine squared is equal to 1 minus cosine of 2 theta over 2. We can convert this. Convert this into 1 minus cosine 2 theta over 2 from 0 to 2 pi. Okay, in this case, what you're going to want to do is split these two up so that you get the integration of 0 to 2 pi of 1/2 d theta minus the integration of 0 to 2 pi of, sorry, I'm just going to take the 1/2 out. You know what, you're right, I'm going to take the 1/2 out. Who am I talking to? Minus cosine of 2 theta d theta. So with the 1, it's pretty simple. You just get 2 pi. And then with the theta, man, this is really crunching up my work. You get u is equal to 2 theta. So du is just equal to 2. So we get a 1/2. And I'm actually just going to keep it like this, of 2 theta. And that becomes sine of 2 theta. I'm not going to keep it as a u. And then once you evaluate sine of 2 theta between 0 and 2 theta, you get sine of 4 theta minus sine of 0, which is all equal out to 0. So in the end, you just get 2 pi. Don't forget that 1/2 just becomes pi. So after all this, we get 18 plus 0 plus pi, which gets us 19 pi. And then finally, that 1/2 comes back, and our final answer becomes 19 pi over 2. Wow, this looks like the work of a madman. But in this case, our answer is answer choice E, 19 pi over 2. All right, moving on to question 18. So, question 18 looks like a simple double integral, but if you look at this first part, you notice it is actually impossible to integrate e to the power of x to the power of 5 with respect to x. It is directly impossible. So, in order to do this, we'll have to change the order so that we integrate with respect to y first, so that a y will appear that makes the x integration possible via u substitution. So, let's sketch this out here, right? Our current bounds are dx between y square root of y, which would look like this, and x equals 1. And from y, it just goes to 1. So 1, 1. These are our bounds right now. We want to change our bounds, so instead it's like this. So instead now, we'll say that if x 1 comma x less than square root of y, we're going to say that if x is equal to the square root of y, then why is y not just equal to x squared? Amazing. So if we look at our graph here, now we see that y goes from 0 to x squared, and x simply just goes from 0 to 1. How does this change everything? Well, our integrand stays the same, but now, oh, my Apple Pencil changes from dy to dx. So let's evaluate this. So now it's dy. We get y squared over 2 evaluated from 0 to x squared, which gets us x to the 4th over 2 minus 0. So that's all we're left with. Now we have to evaluate from 0 to 1 of x to the 4th minus 2 times e to the power of x to the power of 5 dx. In this case, this is where you do a u substitution of u is equal to x to the 5th power, and du is equal to 5x to the 4th power. We have an x to the 4th power, so what I'm going to do is I'm going to multiply it by a 5, which leaves us with a 1/5 du. So we have a 1/5, and we're going to change our bounds. So when x is equal to 0, u is equal to 0. When x is equal to 1, u is still just okay, so they're the same. It's just 0 to 1 of 1/2 eu and that's that. So you just get eu between 0 and 1. I'll combine these to get 1/10. Just gets me e to the power of 1 minus e to the power of 0, which is just e minus 1, all divided by 10, which gets me the answer choice C. Now, in this case, this is one of those problems where I would suggest drawing it out first and seeing, is that really possible? Is the integral possible first off? Especially when you have an integral as simple as this. In this case, draw it out, change the order of integration, do these u substitutions, and get your answer. And that was question number 18. Okay, moving on to question 19. Last two questions. Good job. So, question 19 asks, for the vector field f vector of z minus y squared in 2x, compute the double integral of vector f times the normal vector ds across the flux through the surface x, given that the graph z equals x squared over the rectangle where x is between bounds 0, 3, and y is between bounds -1 and 1, with the normal vectors oriented upward. Now, what I notice is that this question is really good at putting a whole lot of words and confusing people, but I'll try to simplify it down. Flux basically measures how much of a field passes through a surface. So for a surface like this, where z is equal to xy, the flux is simply just the double integral of the dot product between that field and the normal vector. So there's a few things we need to find. Of course, we need to find that normal vector ds. We need to substitute z equals xy into the vector f. We need to dot f and ds. And then we just need to integrate. So let's do that. So same thing as we've done before. When z is equal to xy, we got to find the partial derivative of z at x, with respect to x, which in this case would just be y. The partial derivative of z with respect to y, in this case, will just be x. Amazing. So in order to find this, remember that the normal vector is negative z of x, negative z of y, and just 1. So when we plug that in, you get negative y, negative z, and then 1. Sorry, not negative z, negative x, and then 1. Okay, so that is your normal vector. Now, we got to substitute z equals xy into f. So we know that f is equal to z negative y squared 2x. So how do we substitute this in? Let's see. So we know that z is equal to xy. Negative y squared, in this case, is still just negative y squared. And 2x is just 2x. In this way, we're keeping z out, and we're just evaluating x and y because these are the bounds given to us. Okay, so let's do their dot product. Let's dot the vector f with its normal vector. So you get xy, negative y squared, and 2x, all dotted with negative y, negative x, and 1. which gets us negative xy squared plus xy squared plus, well, that's not squared, plus 2x. These two cancel out, which simply leaves us with 2x. Okay, so in this case, now all we have to do is do a simple integration. So choose what bound you want to do, but since there's an x as the integrand, I choose to use dx first. So x goes from 0 to 3, y goes from -1 to 1, which simply gets us x squared evaluated between 0 and 3, which gets us 9 minus 0. And then once we evaluate 9 between -1 and 1 dy, you simply just do 9, and then that's just 1 minus -1, which is 2. So 9 times 2 gets you the answer 18, which in this case will be answer choice A. And that was question number 19. Okay, moving on to the final question of this long exam, question 20. Question 20 asks us to find the double integral of the function f of x, y, z ds, where the function f of x, y, z is equal to z plus 4x, and s is the surface given by z equals 8 minus 4x minus 8y, with x is positive, y is positive, and z is positive. So by them giving us that information, we know that this is an integration problem restricted to the first octant, which means that everything is positive as stated. So the first thing we're going to want to do, since we're restricted to the first octant, is find a projection, let's call it a D, on the xy plane, which means we set z equal to 0. So in this case, z is equal to 0, which means that x minus 4x minus 8y. So 8y is equal to 8 minus 4x, which means that y is equal to 1 minus 1/2 x. Okay, keep this in mind for now, because the second thing we're going to do is set up a surface integral formula. Now, you've already seen this a few times in this exam, but it'll be f of x, y, and I'm introducing g of x, y. You'll understand later. And this is all multiplied by that big formula that I showed you a couple questions ago. Squared plus dz over dy squared plus 1 dA. Now that is a massive formula, but we can break it down. We know that dz over dx is just the partial derivative of this. In that case, that's just -4. And dy dx, oh my god, I'm actually like so bad. dz dy in this case is just the partial derivative of z at y with respect to y. In this case, it's just -8. So we gotta just calculate this. That'll just be -4 squared plus -8 squared plus 1, which is the square root of 81 dA, which just ends up getting us 9 dA. Okay, so now that we have this, all good, we got to figure out the rest. So in that case, we know that f of x, y, z is equal to z plus 4x. But we also know what x is. X is 8 minus 4x minus 8y, so we can substitute that in. We get 8 minus 4x minus 8y plus 4x, which just leaves us with 8 minus 8y. And this is multiplying the outside, so this will be 8 minus 8y times dA, which just gets us 72 minus 72y. If we substitute the 72 out, we just get 72, 1 minus y. Okay, so now you have this out in your integral. In this case, just becomes, leaving the 72 out, 1 minus y dy dx. Now, I already told you that in this case, since we're taking this projection here, our bounds are just between 0 and 1 minus x over 2. If you want to find what x is, in this case, set y equal to 0. So y is 0 now, 1 minus x over 2. So you get x over 2 is equal to 1, which means that x is equal to 1, which is x's upper bound. Just means you get from 0 to 2. So now we have to solve this out. Once we solve this out, you get y minus y over 2, sorry, y squared over 2, which you evaluate this between 1 minus x over 2 and 0, which gets you 1 minus x over 2 minus, and I'm going to make this look very weird, but this will be 1 minus 2x plus x squared over 4 over 2. Or you can just write 1 minus x over 2 squared if you don't want to do it simply. Okay. Okay, so now that we have this all figured out, we have 1 minus x over 2 minus 1 minus, I'll just call that x because the 2's cancels out, plus x squared over 4 over 2. We can rewrite it as this. 1 minus x over 2 minus 1/2 minus x over 2 plus x squared over 8. Now you might be wondering why the 2's go under. That's because when you divide by 2, it's the same as multiplying by 1 over 2. So when we bring this out, you get 1 minus x over 2 minus 1/2 plus x over 2 minus x squared over 8, which ends up with 1/2 minus x squared over 8. And these two cancel out. Okay, so we've simplified it down to a little bit easier form to read, but now that we have it integrated in y, we have to do the integration from 0 to 2 of x. So that's 1/2 minus x squared over 8 dx, which gets us, oh my god, this will stop moving around, gets us 1/2 x minus x cubed over 24 from 0 to 2, which is 2 over 2 is just 1 minus 8 over 24, or simply 1 minus 1/3, which is 2/3. Okay, so now we have 2/3, which we figured out our integral, but there's still the 72 right here. So we do 72 multiplied by 2/3, which just simply gets us 144 over 3, which gets us 48. And for question number 20, the answer is B, 48. So you did it. That was question number 20. This is a very tough exam, so if you got through it, congratulations to you. Happy Valentine's Day. I wanted to put this picture of my cat because I'm so proud of each and every one of you for getting through this exam. And good luck studying on your finals. I hope everyone gets an A.